Okay, actually, I thought I was done with the last video, but I thought maybe I should summarize some of the things that we've talked about, just to be sure that it's clear kind of the important points that we've been discussing. Um, so, uh, like before, xi through, or x1 through xp will be n points in our p points in Rn. We'll assume that the mean is x bar, and that's also in Rn, and that we also have the n by n covariance matrix C. Very good. So earlier in the sessions, we talked about, I've got the paper here, how does the variance change with projection? And so in that little discussion, we decided to project our variance, or sorry, we projected our data to the vector u. And we found that the variance in the direction of u was equal to u transpose times c times u. Now again, that's the variance of the data projected to the vector u. The variance of the data projected to the vector u. Good. Now, we defined, or if you define xi to be the projection to phi1 plus the error, what we're calling the error, this is actually the projection to the other n-1 basis vectors, whatever those are. Then what we're trying to find is we're trying to minimize this quantity, this error function. So this is called minimizing the reconstruction error. We're trying to minimize the reconstruction error. What reconstruction? Using phi1, right, as the base, or as a basis. And so that's using phi2 through phi-n as the remaining basis. But we said that if I take the norm of all the data points and take 1 over p minus 1, just a little bit of a little scalar multiple of that, then I get phi1 transpose times the covariance matrix times phi1 plus 1 over p minus 1 times the error function. We said this is constant, therefore minimizing the error function is the same as maximizing this expression. And so therefore we don't actually minimize this error function, right? Instead we maximize this quantity. But notice something, that is the variance. So what we're actually trying to find is another way to look at this, number 4, another view is that we find phi1 that maximizes the variance of the projected data. That is projected to phi1, right? And so this is the statistical viewpoint. So if you've taken statistics and you've talked about the SVD, or sorry, not the SVD, the PCA, then this is the viewpoint that you're talking about. So what is PCA? PCA stands for Principal Components Analysis. And so the principal components are the vectors that maximize the projection of or maximize the variance of the data projected to those vectors. Okay, which as it turns out to be our best basis. And so principal components analysis is the same thing as our best basis. I should say that this goes by a lot of different names. I used to call I used to title this the Karhunen-Loew basis, but people didn't know what that was. That comes from signal processing literature. This is called, so finding the best basis is called Karhunen-Loew analysis. It's called principal components analysis. It's called empirical orthogonal functions. It's called What are some other names for it? Um, oh, I'll have to check. But there's like it depends on what you're um, using or what kind of data you're using sometimes. But it goes by lots of different names, and so that's why I've just called it the best basis. It's more generic that way, I think. Good. Okay, so this was meant to be just a short video, just to summarize things and kind of talk about what's going on here. So the best basis, again, is the basis that minimizes the reconstruction error using phi1 as the basis. So it's the n minus 1. It's the reconstruction error in the n minus 1 dimensional space. And so we're kind of subtracting phi1 from our space. And as it turns out, minimizing that error is the same as maximizing this quantity. And that quantity turns out to be the variance in that direction. Good. All right. The end for now. In the next, so I think I've run way longer than I usually do for my class lecture notes. So I think what we'll do is we'll save the big application for Monday. It'll give you something to look forward to. Okay, so I'll put the homework up on the website. It'll just be the homework is really just to look at some of these computations again. I know sometimes it's easy to for me when I start rambling to kind of go off, and so it's good to go back into the paper and see what's actually being said. Okay, I'll stop rambling now.